Let's move on to section 2.3, the standard enthalpy change of combustion. It has a symbol of delta HC, where C stands for combustion. It is the heat evolved when 1 mole of a substance is completely burned in excess oxygen under standard conditions of 298 Kelvin and 1 bar. The enthalpy change of combustion can be determined experimentally using this setup, where the heat evolved from the combustion process is transferred to a metal can with water. The temperature change of water in the metal can is measured in order to calculate heat change Q of the reaction. After calculating Q, the enthalpy change of combustion can be obtained by this equation, which is equal to minus Q over amount of substance burnt. The per mole in the units refers to per mole of substance burns based on definition. To represent the enthalpy change of combustion in a thermochemical equation, for example, for liquid ethanol to undergo combustion, the equation must have 1 mole of ethanol to react with oxygen to form CO2 and water. For metal, example magnesium, the equation must have 1 mole of magnesium to undergo combustion, reacting with oxygen to form metal oxide. So therefore, the thermochemical equation to represent enthalpy change of combustion, the substance to be burnt in the equation must be 1 mole. Note that those substances which can't undergo combustion or cannot be burned will have enthalpy change of combustion to be 0 kilojoules per mole. For example, water, oxygen, carbon dioxide, and metal oxide. These substances do not undergo combustion. All enthalpy change of combustions are negative. The processes are all exothermic. This is due to much stronger bonds that are formed in the combustion product than those bonds that are needed to be broken in the reactants. In fact, the enthalpy change of combustion's value allows us to compare the energy values of the fuel. The more exothermic the enthalpy change of combustion, the higher the energy value of the fuel. A more accurate determination of energy change of combustion is by a bomb calorimeter. This is a bomb calorimeter. Note that it doesn't measure enthalpy change, it measures energy change, because in a bomb calorimeter, the pressure is not constant. It is the volume that is kept constant. So please watch this video from 3.01 minutes to the end to understand how a bomb calorimeter works. Let's look at exercise 7. A student carried out an experiment to determine the enthalpy change of combustion of ethanol using the setup on the right. This is the setup, and the following measurements are taken. Volume of water used is 300 cm3. Initial temperature of water is 25 degrees Celsius. Final temperature of water is 35 degrees Celsius, and the mass of ethanol burnt is 0.750 gram. Assuming that only 70% of heat produced is used to heat the water, which means there are 30% heat lost to the surroundings. Calculate the enthalpy change of combustion of ethanol. Note that we'll need the specific heat capacity of water because it is the water that absorbs the heat from the combustion process. This value can be obtained from the data booklet. It's given to you as 4.18 joules per gram per Kelvin. So to calculate Q, you must use the given C times M times delta T. So Q equal to MC delta T, where M is a mass of water in the metal can, because it is the water that absorbs the heat from the combustion process. And to calculate the mass of water in the metal can with the volume given, you will need to know the density. So mass of water is equal to density times volume. So the heat absorbed by water will be equal to MC delta T, where m is the mass of water in the metal can given by 300 times density times 4.18 times temperature change 25 minus 25.0. The temperature change in degrees Celsius is the temperature change in Kelvin, so do not add 273 to a delta T value. And the calculated Q will be in joules. Convert to kilojoules, that is 12.54 kilojoules. And you are told that this corresponds to only 70% of total heat change, because only 70% of heat produced is used to heat the water. So the actual total heat change from the reaction, you have to step up to 100. So must times 100 over 70, which is 17.91 kilojoules. The amount of ethanol burned will be 0.750 divided by the MR of ethanol. And since temperature rises, the reaction is exothermic, the enthalpy change has a negative sign. So the enthalpy change of combustion of ethanol will be equal to minus heat change, which is 17.91, divided by the amount of ethanol burnt, which is 0.0163, which is equal to minus 1100 kilojoules per mole. Note that the above setup does not give an accurate determination of enthalpy change of combustion. From the setup, you can see that heat may be lost to the surroundings due to convection current, due to air convection. And there could be incomplete combustions of the fuel due to insufficient oxygen supply, because the spirit lamp does not receive pure oxygen supply like in the case of bomb calorimeter. And there could be evaporations of liquid fuel from the spirit lamp, as liquid fuel are volatile. So the mass of fuel burned is not accurate. Let's try exercise 8 together. You are given 1.80 gram of propane ore was used to heat a metal calorimeter containing 250 cm3 of water. The temperature of water rose from 25 degrees Celsius to 66.5 degrees Celsius. Assume that the heat capacity of metal calorimeter to be 25.0 joules per Kelvin, and only 75% of heat is transferred to the metal calorimeter and water. Calculate the enthalpy change of combustion of propane ore. And you are given specific heat capacity of water to be 4.18 joules per gram per Kelvin. So to calculate Q, heat change of water, you must use the given C times M times delta T. So Q equal to MC delta T, where M is the mass of water in the metal calorimeter, because it is the water that absorbs the heat from the combustion, and delta T is the temperature change of the water in the calorimeter. And to calculate mass of water, you have to use density times the volume. Density of water is known to be 1 gram per cm3. So heat absorbed by water is equal to MC delta T, is equal to the volume of water times density, 250 times 1.0 times 4.18 times the temperature change in Kelvin, 66.5 minus 25.0. Note that the delta T in degrees Celsius is the delta T in Kelvin. And the answers for Q will be in joules, convert to kilojoules. The heat absorbed by the metal calorimeter will be given as C times delta T, because it is given as 25.0 joules per Kelvin. To get Q, which has units of joules, you need to use the given big C times delta T. So heat absorbed by calorimeter is big C times delta T, so 25.0 times delta T, which is equal to 1038 joules, convert to kilojoules. You are told that only 75% of heat is transferred to the metal calorimeter and water. So the total heat gained by the metal calorimeter and water is equal to 43.37 plus 1.038. And this corresponds to 75% of the heat from the reaction. So the total heat change, the actual heat change, you have to step up to 100%. So the actual heat change of the reaction will be 59.21 kilojoules. And the amount of propane 1-ol burn is the mass 1.80 over the MR, which is 60.0. That turned out to be 0.0300 mole. And since temperature rises, enthalpy change is exothermic, the sign is negative. So the enthalpy change of combustion of propane 1-ol is equal to minus heat change Q over amount of substance burn, which is equal to minus 59.21 kilojoules divided by 0.0300 mole of methanol propane 1-ol burn. So the answer is minus 1970 kilojoules per mole. So this is a reminder again why delta T of 1 degree Celsius is equal to delta T of 1 Kelvin. So when the initial is 28 degrees Celsius, final temperature is 45 degrees Celsius, the delta T in degrees Celsius is 17. To calculate delta T in Kelvin, if you take 45 plus 273 minus 28 plus 273, 273 will cancel each other. So the temperature change in degrees Celsius is the temperature change in Kelvin. So remember, don't add 273 to the delta T value.